So thank you very much for giving me some time to share some of our recent work in looking at self-adhesive elastic fabric sensors for monitoring essentially physical performance. Before I begin, I'd like to acknowledge the different students who contributed to the work that I'll be showing today. This is just some of them moving from left to right: Emerson, Taylor, and then Shih-Chao and Yujin also contributed, but weren't part of this particular field study that we did in Michigan. Here are my conflicts, potential conflicts, and then of course all the opinions that I share today are just mine, not that of the US government or state. And before I jump into the main aspect of the talk, I'd also like to take this opportunity to share with you what we do here in my group at the Armor Lab. By the way, is there any chance we could turn this down a little bit? The front lights. Sorry, I have a lot of black backgrounds and thinking that it would look a little bit better, but it's actually a little dark. Sure, great, thank you, appreciate it. So at the Armor Lab, our mission is to develop technologies and find methods that can help us better protect and enhance the performance of not just our physical assets, but also our human assets. And in particular, we have two core capabilities: leveraging different nanomaterials and methods to develop stimuli responsive materials. So that's your sensors, actuators, among many other types of materials-based systems, and combining them with interesting inverse problems, algorithms, and data-driven methods to essentially extract as much functionality and information from these materials as possible. So armed with those two core capabilities, we have dedicated ourselves to solving research problems in three main domains. The first of which is looking at structural performance, or helping maintain sustainment of our physical assets. So looking at sensing scans and meshes, that could be applied onto structural surfaces to detect damage, as an example. Second area, and the focus of my presentation today, is to look at human performance, how we can develop specifically wearable sensors or just wearable devices in general that can help improve the performance or augment the behavior of people. Last but not least, we're also very interested in looking at how technologies can help improve the ability for our human assets and the structures to work together more collaboratively so as to achieve and improve their performance objectives. But for the purposes of today's presentation, I'd like to hone in more specifically, not only on humans, but looking at specifically athletes and our tactical athletes. So if we think about what our athletes do, particularly those that compete on a day-to-day basis, there's mainly three sort of core tasks that they focus on, right? Starting with training. And a lot of time, we know that NCAA athletes train about 30 hours a week. NFL football players train more than 40 hours a week. But the goal for them is to train to maintain their fitness, to improve their skills, and sometimes to develop new skills, right? So in terms of monitoring physical wellness, maintaining that level of fitness and trying to optimize that is critically important for these folks. When they're in competition, monitoring performance and fatigue is just as important, right? And very critical. Being able to track when individual athletes needs to be subbed out so that we can maintain their performance throughout the entire game, as an example. And of course, the goal is, during this entire time, be able to prevent injuries from occurring in the first place. But unfortunately, some of our athletes and tactical athletes do suffer from sometimes very serious injuries. So there's a need to develop active rehabilitation techniques that can help them recover and regain those lost functionalities as quickly as possible, right? And that can entail, ensuring patient compliance or just obtaining important data streams for our clinicians and sports coaches to work with. Now, I would say that despite recognizing these problems, if you will, even with all the great wearable sensors out there today, we still lack a lot of the relevant sensing streams that can really provide personalized information for our athletes to help them improve their physical performance and health. So our solution and big vision as part of my group is to develop the athletic digital twin, right, as sort of one subset of everything that we do. And I know digital twins, it's a buzzword that's being thrown around out there. Everybody has their own definition. But for me and for my group, we essentially define it as a system that's able to sense, make sense, and act, right? So our goal is to take the athlete and to create a corresponding digital representation of that. And this digital representation or digital twin doesn't mean that we're trying to develop a detailed finite element model of the structure, right, or of the person, but rather be able to obtain relevant sensing streams, be able to fuse them together and feed them into either a data-driven, physics-driven, or a blended sort of approach to start making sense of that data, those data sets about that specific person, and be able to provide tailored feedback so that we can augment the behavior or training activities of that particular individual. Now, I mentioned earlier that we currently lack a lot of those relevant sensing streams, right? But it's also important to recognize that we do have a lot of tools available to us, right? And they range from commercial wearables like the Aura Ring, that was just previously mentioned, motion capture to get full body measurements, IMUs to get joint rotations, body velocities, angular rotations, etc. Surface EMGs to get muscle activity, and even some of the sort of emerging electronic textiles that look at sort of a dense body sensor network to really characterize movement, right? And they all do these things extremely well. In fact, we use NOCAP and SEMGs as the gold standard for measuring those specific parameters. But what I like to point out is that there are also limitations, right? And a lot of those limitations are essentially summarized here, where you need to use these instruments in specialized facilities and laboratories, and really these controlled indoor environments. But when we talk about our athletes and tactical athletes, considering the diverse environments that they're exposed to, we want to be able to transition and these sensors and be able to collect those data streams when they're just at play, right? When they're in their sort of free living community setting. There's also some data acquisition and processing challenges in terms of sort of the computational demand, as well as hardware, software requirements. But one of the critical aspects that I'd like to touch on today is that for a lot of these on-body sensors, especially electronic textiles, using compression garments or shirts and things like that, they ultimately suffer from movement artifacts, and that's one key point that we're trying to address through our work. So the main sensing sort of element that I wanted to share with you today, the wearable sensor, is what we call motion tape. And what this is essentially a self-adhesive elastic fabric sensor that can be mounted virtually anywhere on skin. And our approach to sort of designing this from the get-go is that we want to move beyond just having our wearable telling us whether or not we're moving. So something like my Garmin watch telling me how many steps I'm taking in a day, to looking at what it is that people are doing, how they're moving, such as what we can get from motion capture, but go even further and be able to extract how our muscles are engaging in order to produce those functional movements. So our approach to creating this motion tape is by leveraging sort of our capabilities in processing different types of nanomaterials, creating these coatings and thin films out of them. And for this work specifically, we've decided to use commercial kinesiology tape as our substrate, since they figured out exactly how to get that sticky fabric onto a person and have it last for quite a long time. So by developing the appropriate ink formulations, we can use very low-cost, scalable manufacturing methods, such as spray coating or inkjet printing, be able to deposit and pattern and integrate these nanocomposites directly onto these elastic fabric. And once we've had those prototypes, we've conducted a suite of laboratory validation studies and basically showed that these materials behave as excellent strain sensors, specifically skin strain sensors, with very high sensitivity and linearity. To facilitate some of the field collection work and just to make things a little bit easier when we work with our human subjects, folks on my team have also designed various different generations of electronic data collection modules. Shown here are just two examples. So on the left-hand side, we have a sort of a single channel sensing module that collects all the data, stores it locally on a micro SD card. This was particularly useful when, as part of this particular work, working with some of the Marines, we had to essentially store the data locally, right? So this system, is self-contained, and then we could just pull the data at the end of each day. On the right-hand side is something that we use more frequently nowadays. It's a little bit more convenient. Connect 8 different channels or 8 motion tape sensors to it, collects data simultaneously at a fairly fast sampling rate to capture many of the different types of dynamic activities that our athletes go through. It's powered by a single point cell battery and can stream data in real time over Bluetooth, so we can visualize data as we conduct our various tests. But essentially, with the motion tape sensors, with the data collection units, and some of the laboratory facilities that we've had, we also had the opportunity to go through a lot of IRB-approved human subject verification studies. So shown here is an example, some of our earlier work looking at, can we capture joint rotations and comparing those measurements to video data to extract joint angles. We can also take motion tape, instrument a bunch of them to form these unique patterns over specific muscle groups, such as in this case, the middle deltoid, posterior deltoid, and triceps, and collect data while our subjects are going through different types of physical activities, such as tricep dips, push-ups, or other types of physical exercises. The point here is to show that depending on where these sensors are mounted on the skin and what specific activities that individual participant is doing, we can obtain unique sensing streams associated with how those muscles are engaging in order to produce those functional movements. But it's also important for us to demonstrate that the skin strain measurements that we're getting are in fact accurate, right? So to do that, we've leveraged our optical motion capture system in the lab, picked two relatively flat anatomical regions on the body, in this case, the calf and the tibialis anterior, so relatively flat. We can mount motion capture markers adjacent to those films so that we can begin to calculate the estimated linear strains in that particular region and compare it to some of the measurements that we're getting from motion tape, right? And overall, we're seeing that the sensors behave linearly as expected with low hysteresis. It's also important to recognize that our approach to estimate linear strains is not exactly 100% accurate. There's a lot of assumptions made, when we're doing that. So overall, we're pretty happy with the results. But a little bit deeper dive into some of the data sets that we collected show that this is not just for one particular test or one particular subject. In fact, we're seeing fairly high correlation coefficients, and the sensors also respond fairly quickly to human movement. Now, I also mentioned earlier that our goal is to not only be able to use that data to see what people are doing, but also potentially understand how those muscles are engaging in order to produce those movements. So with the high sensitivities offered by these skin strain sensors, we hypothesize that perhaps we can capture minute skin strain differences as a result of the degree of muscle engagement. So in this particular test, we had one piece of motion tape mounted to the biceps. Adjacent to that is a EMG sensor. And we also had a couple of IMUs to measure essentially to extract the elbow angle as we asked our subjects to perform bicep curls. From our data that we collected, we found that, in fact, depending on the weight that the participant is trying to lift while performing those bicep curls, we saw a correlation where the motion tape results, particularly the magnitudes of the data, scaled and increased in tandem with our SEMG sensors, right? And while showing that our athletes were able to pretty much do very controlled bicep curl movements with the elbow angle change, pretty fixed around 51 to 52 degrees. And this is also not just unique to one subject, but across multiple subjects. We also wanted to show that this is not specific to one particular body region or muscle group. So we moved our essentially sensor pair away from the biceps to look at, in this case, the forearm, and again, found similar levels of correlation. So hopefully through this sort of high-level quick discussion, you can start to imagine that there's many different types of use cases where we can apply the self-adhesive fabric material to start understanding how people are moving. And combined with signal processing, machine learning methods, and data visualization techniques, there's many use cases that we could start to look at. And in fact, we are. So we can use motion tape for essentially assessing people's physical health or physical activity, look at assessing people's posture or ergonomics. helping our athletes tailor their training activities to improve performance, or even potentially help people go through physical therapy and rehab by providing them with very specific feedback on how they are moving. So what I'd like to do next is to kind of just go through a quick example of each of these, and then wrap up. So for physical health monitoring, one of the things that we've kind of focused on is to look at respiration, right? Because respiration is a very important metric in terms of deriving additional information about somebody's health, endurance, and their ability to perform these various duties. In addition to using motion tape directly on skin, we've also looked at incorporating motion tape onto sort of commercially available elastic band materials to make it more convenient so that we can take the system, hand it off to person, and just have them go through their daily activities. In addition to showing that the data streams that we're getting from either approach is well correlated to some of the commercial devices out there, we can also apply sort of interesting signal processing techniques to start to extract more detailed information just from one sensing channel, right? Specifically using Wearable transform-based methods to show that we can figure out the rate at which people are walking or jogging simultaneously to getting information about their respiration rate, and then comparing that with some of the known parameters that we're subjecting our athletes and participants to. I also mentioned that we're very interested in understanding people's posture and ergonomics. So in addition to sort of ergonomics, there's other applications where posture can help us infer what people are doing. And we're looking at this from a shipboard sailor standpoint, especially in the damage control and firefighting scenario. But in this test, we can have our subjects wear, 2 pieces of motion tape sort of near the neck trap area. My video is playing, but it's very subtle, right? So you see a subject kind of tilting their head up and down, and then left and right. But essentially, just from looking at the raw time history data streams, right, you can begin to see those asymmetrical type of responses that you would expect depending on the directionality of where that head is turning. Similarly, we could look at sensors on the abdomen, right, where we go through sort of different bending and twisting type of movements. And again, from the raw data streams, you can see regions where things are in phase versus out of phase, as you would expect, right? Just showing that, this is a preliminary sort of data set that we're looking to extract posture information. Now, I do want to spend a little bit more time on this, and Patrick and Joe, feel free to cut me off if I'm running low on time. But I did mention that we are trying to develop the athlete-human twin, right? And specifically extracting sort of useful information that we can then digest and be able to help our athletes augment their behavior to improve their training. So one of those areas that we focused on is improving the soccer kick. Can we, through this approach, begin the steps to start digitizing sports coaching? So with our subject, we recognize that in many sporting events, and specific to soccer, this is a full body engagement, right, to try to kick a ball, right? It's not just about sort of moving your leg. So we've identified sort of key areas on the body, applied essentially pairs of sensors near the pectoral regions, the waist, or the abdomen area, hamstrings, knee, and the ankle, right, to try to capture sort of those movements during kicking of the ball. So the task here, and specific to this test, is pretty simple. It's a single hop kick of a soccer ball surrogate. Actually, I'll show the picture right here. So we're doing this in our lab, and we don't want to destroy our instruments. So the single hop kick is, right, we have a balloon, we have onto some markers, you line up to it, and basically take a step back, and then you try to kick it as hard as possible. Okay, so this particular participant that we work with has no interest or experience with soccer, which is great. So we can get our baseline sort of untrained response, right? Collecting data from a full body motion capture data set in addition to the sensors that I mentioned. Our sports coach that we work with then told us that, well, there's a simple sort of task that we can do to help people improve kicking. And I can swear to this because I've tested it on my kids. It might be time and not energy I read. And that is going through the same motion, right? If you just raise your other arm, meaning your so my dominant side is my right, so there's my left hand, left arm. And just kind of keep it up, right, the entire time as you hit the soccer ball. And, let's see what happens. Right, so those are kind of that's what I call the novice versus the coach response. So these two videos show you what we've collected from our motion captures, kind of illustrating that same motion, right? So this is the uncoached, and this is the coach response, and you see those additional points showing that the arm is up, right? So they look the same. And these are some of the sort of time history data that we can collect from our sensors. So here, the red corresponds to the coached, and the blue corresponds to the uncoached or novice response, right? And even just looking at sort of these positions, so on the waist or abdomen area on both sides, we see that just by lifting our arm up, we can see much greater sort of that torque and twisting movement that really contributes a lot to improving the kicking speed, or the kicking the soccer ball to maximize the ball speed, right, which was our goal. And in doing so, by having that sort of arm up, that moment arm up, from a biomechanical standpoint, as your body tries to compensate for that eccentric weight, the right knee becomes much more engaged earlier on to deliver that powerful kick. So just from these, time history measurements, we can observe, sort of key differences just by looking at these time history signals to show that these minor changes in behavior can really help people improve their athletic performance. But this is us looking at it from a time history perspective, right? Because ultimately the goal is that we want a system that could be able to do this automatically as we get additional data. So a part of my team is looking at, can we use data-driven methods, in particular machine learning algorithms such as this deep convolutional autoencoder, to essentially train it using the ideal or correct responses. So movement sequences that delivered good results, and also at the same time where the athlete felt good about doing that, right? I won't go into the details of the algorithm itself, but essentially leveraging an unsupervised technique to start to be able to process these data sets automatically. Now, I mentioned soccer previously as an example. This work is funded by the Navy through various projects. So a big part of that is looking at sort of more military-oriented applications. So we looked at cases where how people can shoot, or at least point and shoot a rifle correctly. On the left-hand side is trying to hit a target that's directly in front of you. On the right-hand side is turning and then also delivering that kill shot. The point here is that there's correct ways and incorrect ways to do it. Typically, it involves how your head moves. So we can collect, again, similar to that soccer case, movement sequences or movement data near the neck from motion tape. And on the left-hand side, the differences are a little bit more subtle, right? But on the right, certainly we see sort of key differences that we can identify from the time history. But regardless, by taking these data streams, throwing it into our trained machine learning algorithm, we can now be able to identify exactly whether or not a movement sequence has been done, quote unquote, correctly, but more specifically be able to pinpoint when movement deficiencies occur, as shown by the sort of orangish red section, right? And depending on where our motion tape is mounted, be able to provide body location specific feedback, right? So in this case, the neck. So in the forward rifle shooting test, this corresponded to sort of tilting your head excessively, and that led to poor performance. And on the right-hand side, this is turning your head ahead of turning the body to deliver the shot. So overall, as we continue this work, our goal and the preliminary results show that we have an opportunity to see when and where movement deficiencies occur during these different types of training activities. Last but not least, and sort of pivoting a little bit, in addition to sort of developing sensors that are powered, that give us information about how people are moving, we're also very interested in rehabilitation and just preventing injury from the get-go. So one of those sort of injury mechanisms that we focused on is to look at lateral ankle sprains, right? And as you can imagine, it's one of the most common in sports and athletics. And oftentimes, ankle braces are prescribed to help with that. But the problem is, sleeves, very flexible, are comfortable, but they don't provide a lot of support. Stirrups can provide a lot of support, but they're very uncomfortable and can affect gait. So our goal was to see if we can sort of find a blended approach, one that is low profile, fits in a typical boot, be able to provide comfort, but at the same time, deliver support when support is needed, specifically allowing free movement during low intensity activities and providing a lot of support during the more intense physical activities, such as during playing in a game. So essentially, we can create these sort of patterned two-dimensional materials, mechanical metal materials that exhibit interesting material properties, incorporate them into these ankle brace sleeves, such as the one shown in the middle, and show that our prototypes are able to provide that low level of stiffness during low intensity activities. But as your ankles get strained to large angles, we provide that additional stiffness to better protect them. So with that, I'll close. I know I'm running a little bit over time. So our path forward in terms of all the activities is to help our athletes and tacklees improve their performance, health, prevent injuries, and help enhance their resilience. So with that, thank you very much, and happy to take any questions.
Maybe time for one question to Ken, please.
Yes, my question is about data acquisition. Is it wired or is it wireless?
Yes, sir. So currently the sensors are connected to our data acquisition node by wires, or just printed sort of structures on the fabric itself. But then the data is transmitted wirelessly to a computer or a phone.
Final question?